everyone, welcome back. We've been doing some really good work with chirality and finding chiral centers in molecules. We were just beginning to discuss pairs of enantiomers, those molecules that are non-superimposable mirror images. And we're going to practice how to draw a set of enantiomers. So let's begin with just an example where we're asked to draw two enantiomers of a molecule, 2-butanol, in 3 dimensions around the chirality center. So just to kind of pick up where we are in section 15.3, practice drawing a set of enantiomers. If you notice that we're just looking at page 5 at the very top on your notepad page, just to help you there. So as we begin drawing, we want to think about a molecule in a 3-dimensional way. So let's find that chiral center. Here's the carbon. And we can clearly see that it has 4 unique attachments. We have an ethyl group in one direction, a methyl group in another. Here we have a hydrogen and of course the hydroxyl group, creating 4 unique attachments. And therefore we have indeed met the criteria of a chiral center. To draw one enantiomer, I just want you to draw the carbon. That's the chiral carbon in the center. And we'll just randomly select the hydrogen and the methyl group to be in the same plane. So I just know that each chiral center with its 4 unique attachments, of the 4, 2 of them lie in the same plane. I'll make the hydroxyl group, the OH, point out as a wedge, and of course that would leave the ethyl group to be the dash going behind the page. So just draw one enantiomer by placing the 4 different groups on opposite corners using the dash wedge structure. So I'll call that structure A. In structure B, which will be its mirror image, imagine that we're drawing the mirror image as we're looking at the molecule through a mirror. And now notice that what's closest to the mirror would be the ethyl group, still in its position of being a dash. So we'd have CH2, CH3. Pointing out still, but closest to the mirror, would be the hydroxyl group. You would have the methyl group in the same plane, but pointing in the opposite direction. We have just drawn a mirror image, a non-superimposable mirror images, 2 enantiomers of one another. So that mirror image arranges the substituents in the mirror so that the reflection is from structure B is the reflection of structure A. Now let's kind of verify that. Remember how I said let's just assign priorities. I'm going to call, let's say the OH, I'm going to call that number 1. So again, I'll just make sure I number them the same order on both mirror images. I'll go to the ethyl group next and call that number 2. And then I'll just number the methyl group as number 3. Remember, I only have to connect 3 of the 4 substituents to see which way those are rotating. Now just simply connect your numbers. 1, 2, 3. Structure A is rotating those in a counterclockwise fashion. And I'm abbreviating CCW, counterclockwise. And when I attach the priorities numbered as we did, in structure B, this is a clockwise rotation. Since A is rotating counterclockwise around the chiral carbon, and B is rotating clockwise around the chiral carbon, these are indeed enantiomers. And I spelled it wrong. Enantiomers. Enantiomer. And that means that they are indeed non-superimposable mirror images. So to repeat those steps, we drew the chiral carbon and just arbitrarily assigned the first center. Doesn't matter where I put those 4 groups. You can decide how you want to place those 4 groups. In this example, we see that the methyl was placed in the same plane pointing up. We see that the ethyl was placed in the same plane pointing kind of bottom right. They made the wedge the hydroxyl group and the dash as the hydrogen. Imagine the reflection. That chiral carbon in this example would have the methyl still pointing up. Coming out towards the mirror as a reflection would be the dashed hydrogen. Here is the wedged hydroxyl, and then still in the same plane, we can see the ethyl substituent group, CH2CH3. And we can again verify that they are spinning in opposite directions. Let's call the hydroxyl group, group number 1, and I number them the same on both enantiomers. I'll make the ethyl group, group number 2, just number them the same. And then this time we'll make the methyl group up here, number 3. And now just connect the numbers. 1, 2, 3, that's a clockwise spin. Here, 1, 2, 3, that is a counterclockwise spin. So again, we have proven that these are enantiomers, non-superimposable mirror images. Draw one enantiomer by arbitrarily placing the 4 groups at opposite corners of the tetrahedron. You will then draw its mirror image. You're creating its enantiomer by drawing the mirror image so that they're a reflection of the first molecule. And you can test your structure by checking the spin. Arbitrarily decide what groups you want to have represent group number 1, group number 2, and group number 3. Just make sure you're assigning the same number to both structures, and they should absolutely spin in the opposite direction. A and B are non-superimposable mirror images, known as enantiomers. Well, let's take a peek at some examples. Locate the chirality center in each compound and draw both enantiomers. Well, I have 1, 2, 3, 4 carbons in that chain, and at carbon 2 we have a chloro group. This would be called 2-chlorobutane. At carbon number 2, that's my chiral center. Do you see how it has 4 unique attachments? One of the attachments is leading to a hydrogen. One of the attachments is leading to a methyl group. One of the attachments leads out to a chlorine. And the last attachment is an ethyl group. I randomly selected where I place those 4 unique groups around the chiral center. It absolutely does not matter what you decide to place on the dash, the wedge, or those bonds that are in the same plane. This is called, we'll just say now, in terms of the first of the 2 enantiomers. Now draw what you would see in terms of the reflection for the second compound. There's my chiral carbon. Still pointing straight up is the hydrogen. The methyl group is still in the same plane, pointing out of the mirror, kind of away from it. Closest to the mirror would be this ethyl group, CH2CH3. And still as the wedge would be the chlorine group. Let's test to make sure we've created 2 enantiomers by assigning numbers and testing the spin. I'm going to call the methyl group number 1. Just make sure you've numbered them the same on both enantiomers. Let's call the chlorine group number 2, and number 3 the ethyl group, just so they're numbered the same way. Connecting this, we have a counterclockwise spin, and connecting these, we have a clockwise spin. We have indeed produced enantiomers. Now, as you go deeper into organic chemistry, we'll learn about an R and an S configuration around a chiral center. R stands for a right-handed spin, and S, which represents the word sinister, represents a left-handed spin, clockwise and counterclockwise. And the order of priorities is assigned based on atomic number. The highest priority gets a number 1, which is the largest atomic number. The lowest priority gets the number 4, and it's the smallest atomic number. There, we've written that out. So the priorities: highest atomic number, priority number 1. Lowest atomic number, priority number 2. And if you have like atoms, keep going until you see the first point of difference. So for example, if I just reconsider how I assigned these priorities, there really is a deeper level we could go to here and learn the R and S configuration. We could see that chlorine has the highest atomic number between, here's the 4 attachments. We have a hydrogen, we have a methyl group, we have an ethyl group, and we have a chlorine. So you can see the order of priority. The lowest atomic number is hydrogen, it's number 1, so it actually gets the lowest priority. Its priority is number 4. Here's carbon, and carbon attached to 3 hydrogens would be the next lowest priority. And then looking at, this is a carbon attached to 3 hydrogens. Think of it that way, CHHH. And this carbon is attached to another carbon attached to 2 hydrogens. So it actually has a higher priority. And of course, the largest priority there, the biggest atom, would be chlorine. So as you're assigning priorities, chlorine would be number 1, ethyl would be number 2, methyl number 3. Connecting those, and we get a spin. And if I re-examine 1, then 2, then 3, and I get the opposite spin. I'm letting you know, if you dive deeper into your organic chemistry lessons, there really is an organized way of designating the spin on the chiral carbon. An R spin is clockwise, an S spin is counterclockwise, and those priorities are based on atomic number. Now, that is not part of our testing objectives, but I wanted to share that there is a system to designate R and S for clockwise and counterclockwise spin. Our course focuses simply on identifying chiral centers and making sure you're drawing enantiomers by checking the spin, but you will not be asked if it's an R or an S configuration. But I did feel an important part to share with you that in a deeper organic class, there is a way of learning how to prioritize and name correctly the spin if it's clockwise or counterclockwise. Now I think there's another example there. So let's be sure we do all of the examples on this page. Let me clear the page and we'll try letter B. All right, so now letter B, we're just going to practice where our level is. We're going to identify the chiral center. The carbon that I highlighted in red has 4 unique attachments. One of them is a hydrogen. I'll just put that straight up. One of them is an ethyl group, right? The CH2CH3. I'll make the wedge, the hydroxyl group, the 3rd attachment, and I'll make the dash the CH2OH. So I have just arbitrarily decided what I wanted on the 4 attachments of the carbon. It is not important to have it just specifically one way. You can decide however you want to attach those 4 attachments to the lines. So we've just drew the first chiral carbon and arbitrarily assigned dashes and wedges to 2 of the 4 components. Draw its mirror image. The reflection in a mirror would have the hydrogen still in the same plane pointing up. It would have the ethyl group still in the same plane pointing away from the mirror, just as it is on the left. Closest to the mirror would be our CH2OH group. And coming out still as the wedge would be the hydroxyl. We can test the spin. I'm going to call the hydroxyl group priority 1. Just make sure you're naming those, assigning the priority groups into the same, and you'll have the clockwise, counterclockwise test work perfectly each time. Priority 2, I would give to the CH2OH, and priority 3, I would give to the ethyl. Again, however you number them is not important for this course, simply to make sure you're numbering those the same way. If hydroxyl's number 1 in the first enantiomer, hydroxyl better be number 1 in the second enantiomer. And we can see that we have a counterclockwise spin in our first structure. We have a clockwise spin in the second structure, Therefore, we can prove that we have made enantiomers. What about chiral carbons that are in a ringed structure? Let's decide how to locate chiral centers and just put them through the same test, regardless if they're in a straight chain or in a cyclic ring. So let's ask ourselves, here's a carbon. We have a 5-membered ring, so cyclopentane. And notice there at carbon number 1 is the methyl group. So we're just simply drawing cyclopentane, 5-membered ring, and wherever you put the methyl group, that automatically becomes carbon 1. So methyl cyclopentane. Does this contain a chiral carbon? Well, I can check this carbon right here. I can see it has, like if we said C1, I can see one of the 4 attachments is a hydrogen. I can see the second of the 4 attachments is a methyl. Let's keep going to see if we find a point of difference. Along the ring structure, what I've colored in purple are the same. It's a CH2. So I have a CH2 in both directions so far. No point of difference. Go one further. If I go one further, it's still a CH2. No point of difference, and I've run out of carbons. Therefore, these 2 attachments are the same, and therefore that does not meet the criteria of being a chiral center. It only has 3 unique attachments. It requires 4. So I do not see a chiral center in methyl cyclopentane. How about another example? What about 3-methyl cyclohexene? So let's draw that together. Notice we have carbon 1, 2, the priority goes to that double bond. Here's 3, 4, 5, 6. A 6-membered ring. And on carbon 1 to 2 is the double bond. And that puts the methyl group on carbon 3. I want to examine this carbon. So we're going to examine with you carbon number 3. What are the 4 attachments on that carbon? Well, I see one of the attachments is a hydrogen. I can see a next attachment of the 4, which is a methyl. When I go from the ring structure, carbon in position 2 is a double bonded carbon, which is a point of difference from carbon 4. In this direction, carbon 3 is attached to another carbon by a double bond. And in the opposite direction, this way, I can see that I have carbon simply attached to another carbon in a single bond. That makes those groups different. This does indeed meet the criteria of being a chiral carbon. So highlighting our chiral center right here at carbon 3. Those 2 carbons are indeed different in this position. This carbon, when I go up in this direction, leads me from a carbon to carbon double bond. And that's very different than a carbon to carbon in a single bond. Of course, you would see that there's 2 hydrogens here, 2 hydrogens here, whereas this only has 1 hydrogen in each direction, making them, yes, very different. Draw the enantiomer of proline. So now we're going to start imagining that mirror and drawing a reflection. So just imagine you're drawing a mirror here, and what would you see? Well, closest to the mirror still appears to be the OH group, and it's leading to a carbon, that's this carbon, which is going up to a double bonded oxygen, coming out of here as a wedge, trying to draw best I can. I see that I now am joining a cyclic structure. So now I'm at this carbon. That's a 5-membered ring, a cyclic structure. Oh boy, that didn't come out very good. I'm going to start over. Try my best to just draw in the mirror image. So this carbon, which I'm highlighting here, leads to a double bond oxygen. I then see that it has a wedge that I'm trying to draw in that leads to a cyclo structure with 5 members, and down here would be the nitrogen. And I'm drawing here the hydrogen coming back to the mirror, and of course this has a little hydrogen there as well. I did my best to draw a mirror image, and it's just really a reflection of what I'm seeing. So that was my attempt at drawing the enantiomer. Put a mirror here and draw its reflection. Since the hydroxyl group is closest to the mirror on the left, the hydroxyl group is still closest to the mirror on the right. We still had the kind of thinking about that symmetry there. Here's the wedge coming out here. Hydrogen still as a dash, and the NH group showing that reflection. So we had one chiral center. That chiral center had the stereochemistry drawn around it. So did you find that? Did you recognize that it was this carbon that was in terms of, oops, I put a crayon. This carbon here, that was the chiral center. Excellent. It's kind of fun, just drawing mirror images. And try another. Oh, this is a great example. Now instead of an enantiomer, we're going to try a constitutional isomer. And that's just on purpose to make us remember all the working vocabulary we've been working on. So instead of drawing a mirror image, we want to draw a molecule that has different connectivity. There's lots of choices here. I mean, any which way you can just move atoms around and still have just, the same number and kinds, but now attached in a different order. So what do you want to do? Get some choices. Golly, I can move the location of the NH group in the cyclic ring. I can move the location of the OH. I mean, you have so many correct choices. Here's one idea. We can just take this COOH, and instead of having it on the carbon here, we can actually attach it to something on the ring. That's one example of many possible ways. The only criteria is that you use the same number of atoms of each element and connect them in some sort of different order. So as an example, if we took the entire attachment off of the chiral center, just one idea, here's the COOH group, right? COOH, and instead of having it attached to create this chiral carbon here, let's just attach it here. And now this chiral carbon has existed. So we moved it from, the chiral center moved from the first position away from the nitrogen to the second position away from the nitrogen, making it indeed a different compound, a constitutional isomer. We moved the chiral center from position 1 to position 2 away from the nitrogen. Lots of correct choices. How about practicing on your own for a moment, taking a peek at all the chirality centers in the following cyclic structure? Just try these on your own, pause the video, come back when you're ready to check. All right, well, let's come back. How did we do? Recognizing a carbon that has 4 unique attachments. I want to highlight that you can eliminate any type of carbon that's in a double bond. They will never be involved in a chiral center. You must have 4 unique attachments, and so if you see carbons in a double bond, don't even consider them. So they're not important for this decision. I want to find a carbon that looks like it has some different things attached. So in my first structure, I notice that this carbon highlighted in yellow is attached to a hydrogen, a hydroxyl. Then I notice it's going to go to points of difference. When I go up the chain, the carbon is attached to just, the next carbon, and I don't see a double bond. So it's a carbon in a single bond. But if I head in this direction, the carbon is involved in a double bond. Those are different, aren't they? That if I start heading in this direction, I get a carbon in a double bond, whereas if I head upwards, that's a single bond. Those are 4 unique attachments. I hope you highlighted that this yellow carbon right here is indeed a chiral center. How about letter B? What'd you think? Well, I mentioned you can eliminate any carbon that's in a double bond, so that's none of this in the cyclic structure. This carbon is attached to 2 hydrogen. This carbon is attached to 3 hydrogens. Those don't meet the criteria. This is an achiral compound. There are no chiral centers at all. What about letter C? Well, I know I can eliminate these 2 because they're attached to 2 hydrogens, so that does not meet the criteria. So I'm going to ignore those 2. And let's decide about the green and the yellow carbons. Alrighty. So let's call this carbon 1 and this is carbon 2. What's attached to carbon 1? Well, it's attached to a chlorine. It's attached to a hydrogen as its 4th bond. Then I see that I'm going out in this direction, and I can see it's attached to a carbon and a single bond, right? So this is CCHH is its 4 attachments. This carbon is attached to 2 hydrogens and another carbon. This carbon is attached to one other carbon and 2 H's. How about in this direction? Well, it's attached to a carbon that's attached to another carbon, but it's also got a chlorine on it. Oh, that's different, isn't it? Indeed, that's the same test for the green colored, which we labeled carbon 2. They are both chiral centers. They both have 4 unique attachments. So in this compound, we had 2 highlighted, well, they're very similar, aren't they? Highlighted green, highlighted yellow, 2 chiral centers. They mirror each other in the same number of attachments. Carbon attached to an H, a Cl, and a carbon that's attached to a Cl, making these 2 carbons in this direction different from each other, right? Good work. You have some assigned reading at this point to finish off this section. Focus on health and medicine. So looking at your reading, 3-dimensional shapes of molecules, you're going to read and pull out 3 to 4 most interesting points from reading. And then I just wanted you to keep going and think about chirality centers and their importance in the pharmaceutical industry. And you're going to read about some interesting medicines and just kind of use your time there to fill out some of those assigned reading pages. The next type of lesson we come back to is on Fisher projections. So you have all of this reading to do on your own. I'm just kind of highlighting what you're going to see when you open your text. You're filling out a little bit of bottom of page 6 and page 7 of your note packs with your own book. And then when ready, come on back to the lesson and we're going to pick up with page 7. Nope, page 8. Page 8 is the Fisher projections. Do your reading, come on back to this video when ready.